Welcome to the first Sumobot Arduino workshop. The Sumobot team apologizes for the inconvenience yesterday of the Nanos. I was disappointed as much as everyone was, because as a presenter that made this week's workshop content, I wasn't told the bootloader issue. I spoke with the organizers to approve the Arduino Unos which worked, and luckily they were approved. This should avoid the hassle of bootloader problems with the Nano and prevent any future troubles. But look out for a post on MS Teams that has the instructions for overcoming the issue. I will have to go through the Nano because it is part of the official kit. In part 1 of the workshop, we'll go through the Arduino hardware. We'll touch a bit on basic library functions in code, but we'll mostly focus on the hardware, basic interfacing, and also, importantly, the basic structure of an Arduino project, because you can go into a deep rabbit hole without defining your aims, the things that you want to accomplish in your project. In part 2, we'll go more in depth through sensor interfacing, which will require us to focus more on C and C++ basics, the syntax, the way we write code, and we'll use the ILN followers and ultrasonic sensors to aid us with that. I can't cover the motor driver, the L298 controller, because I was told the batteries hadn't arrived, so which means we can't use the motors. But I will try to help with giving tips on debugging and algorithm, and also robot design tips. And without further ado, let's have some fun by making some circuits. I think it's important to define the stuff that we'll be using, and the Arduino is a board with a microcontroller, and the microcontroller is basically a chip that includes a CPU and memory, and from that we can easily interface electronics with our computer, such as our laptop. On board are pins, which you can see here and up here for the Uno, but more relevantly for the Nano, there will be below down there. And again, they allow us to connect to sensors so we can interface them. And as I'm showing here in the webcam, these are the pins. The success of any Arduino project begins with an idea, and the inputs, the logic and computer, and your outputs, as well as the constraints and objectives. And in Sumobot, that would be getting your robot to push the oppositional robot off the ring. And a story that we can begin with is with the success of our robot. And we had to autonomously deposit an egg into a container with IR lights by following a road. The project limit was was $100, similar to Sumobot's. And we sought for ways to get inputs so that we would be able to tell the robot to move to the container and deposit the egg, which was the action. It took us a bit, but we realized that the road contained boundaries which were colored black, and we could use IR, infrared, to tell the robot, because infrared is absorbed by black and reflected by other colors, and so we could use that to tell the robot whether it was on its trajectory or not. And we could use that to tell the computer to either turn left or right, which would bridge our logic and action. And the only problem we needed to solve was to deposit an egg into the container. And bear in mind, the container was small, so we had to do it accurately too. And since there were IR lights, IR LEDs, it was relatively straightforward. It didn't have a receiver on the end, so we had to instead make our own receiver in order to get the IR light as an input, and then tell the robot to stop moving and open its gate and deposit the egg. Since the vehicle had to deposit the egg accurately as well as follow the road without veering off course, we needed to separate those two functionalities into systems. and we achieve that using a system diagram to help us shape our objectives that we needed to attain, and in turn our idea of the car. And an example of a system diagram would be the one we made, and in our system to get the car moving on the trajectory, we used essentially a speedometer. It's called an optical encoder, and we also use an IR line follower, which you guys will also have, to help the robot move in a straight line. We also used an IR receiver for the unloading system to tell the vehicle to stop and deposit the egg. And by modularizing our functionalities into subsystems, we were able to develop two prototypes, and the first being partially functional, but the second covering all the necessary requirements for final testing, and in turn allowing us to succeed, all because we followed these three principles of starting with an idea by getting our inputs first, our logic and computer, and our output from our constraints and objectives. With the hardware of the Arduino Nano, we are dealing with the microcontroller chip, the 80 mega 328P, not the 168. You are given the 328P, and the operating voltage for the Nano is 5 volts through the USB port, but below that in the table it says input voltage is between 7 to 12 volts, and you can see in the diagram here the input voltage is actually here, not through the USB port. So right here I have a 3.7 volt lithium battery, two of them, and as a heads up, I've actually scavenged one lithium battery from an old laptop battery, which you can probably do to hint save costs and reduce the budget on your projects. And if I connect the input voltage with the battery terminals along with ground, which is our negative terminal, we should be able to, let me just switch this Nano off. This should switch on and you'll see this power LED go on. Huzzah. So this gives you in your project two options to power your Nano. You can power it on via the USB port, this one here, or you could use the input voltage here and hook it up with ground to some external power supply. But as I remind you that it needs to be between 7 to 12 volts. Before we go on to the digital pins, something that you lot can use to aid in constructing your robot and debugging your Nano if anything goes wrong are to use these status LEDs. The power LED, as the name should suggest, turns on when there's power to the Arduino, like the USB. The L LED, on the other hand, turns on when something is connected to, well, when you use D13, the pin number 13. And that's because if you have a look at the circuit diagram of the Nano, D13 is actually connected to the LED, which means you can actually control the LED and also turn it off or on. The RX LED is connected to the RX pin, and the TX LED is connected to the TX pin. The RX meaning receive and TX meaning transmit. So if any information, if any signal comes through RX1 receive, this LED will switch on. On the other hand, if anything comes out of the Nano, the TX LED will switch on. Let's go apply the status LEDs that we've learned in code. Here I have my IDE, and we're going to switch on the LED, this LED number 13, I'll call it the LLED. And to do that, we should have a look at the Arduino library. and the functions that we could use to help us do that. In order to use the status LEDs, we're going to need to look at the Arduino functions in the Arduino reference library. And we'll do that by typing Arduino reference and click the first one. And this is important because for any project that you do, to achieve some objective, we need to find the functions, we need to find the things that we can do in order to achieve our objective. And the first one, we'll start with this pin mode, and we'll read the description. And it says it configures the specified pin to behave either as an input or output. See the digital pins. We'll do that afterwards. As input pull-up, we don't need to worry about the actual hardware of pull-up resistors. And the syntax and the parameters are the most important. Syntax of the function, meaning the values we input to the function, are pin and mode. And let's see what they are. And the parameters. Pin being the Arduino pin that we need to set the mode of. In this case, we want to set pin 13. And mode, either input or output. Now, pin 13 is currently off, and that's because there's no power going through the LED at pin 13 is currently off, and that's because there's no power going through. Now that means we need to put power through pin 13 in order to switch on the LED. So that means we need our mode to be output. Now we can do that by putting pin mode here and add a semicolon at the end. And I need everybody to exactly write their code in this way, because if you don't, then there will be errors and the computer might misinterpret the code that you've written. And it's pin mode 13, and we're going to put output. And I should also introduce these two sections of code, and I'll introduce this one afterwards. Void setup executes code within these brackets only once. So once it goes from top to bottom, this code isn't executed anymore once it's at the bottom, only once. Whereas in void loop, it is executed repetitively. It will go always continuously rerun itself. Only anything inside this code will be rerun and executed. And we can double check in the Arduino reference, and this should be the place to go when you need to look up for anything related to using functions and achieving your objective. Now, setup states after initialize and sets values. That's correct. Oops. This is loop, pardon. At loop, it does precisely what its name suggests and loops consecutively. As I said before, it repeats itself. Everything inside the code repeats itself. And void setup will only run once. Any code in between void setup will only run once. Now, this here is a comment, and a comment is a place where code isn't run. This here will be invisible to the Arduino Nano. It won't be executed. So we can use this for our own note taking, so we can understand what the code does, and that's mainly the purpose of a comment. And that's going to help us with finishing our code off, because we now want to either begin switching on or off the LED. And in this case, I'm going to begin with the LED on. And the function we'll need for that will be digital write. And let's briefly read it. Digital write writes a high value or a low value to a digital pin. In this case, the output is if the pin has been configured to as an output with pin mode, its voltage will be set to the corresponding value 5 volts for high, so 5 volt or 3.3 volts. In this case, our Nano is 5 volts for high, or 0 volts for low, and perfect for our needs. And the second paragraph, enable, disable internal pull-up. We don't need to know about the the actual hardware, or the resistors inside. If you do not see the pin mode to output, and so if we don't set the pin mode to output and connect to an LED to a pin, when calling digital write high, the LED may appear dim. Again, another hardware thing that we don't need to focus on right now, but the syntax is most important, and parameters. So it's a bit similar to pin mode. We need a pin, the Arduino pin number, and the value, high or low. In this case, we want to start with digital, with on first. Digital write, semicolon 13, and high. Then we want to go low. But recall how I mentioned that the Arduino crystal oscillator is at, it executes instructions at 16 megahertz. That's going to be blazingly fast when it executes this code, approximately 16,000 megahertz. So we won't actually be able to see this turn on and off to the naked eye. And if we try to upload this, which I'll show you using this upload button, but we may need to first configure our board, and I'll do that now. And you do that by going to Tools, going to Board. I've selected Arduino Nano already, but once you get to Board, pardon, once you get to Board, you go to Arduino AVR boards and pick the Nano here. If you're using the Uno, then pick the Uno for yourself. And then we need to go to the processor that we're using. Right now, I'm using the ATmega 328P. You have two versions of the 328P. The old one that I'm using and the current version that most of you will have. That most of you will have. Now, we need to select the port. For me, I remember my COM port to be COM3 because I've used it so much. But for Mac users, you'll see a number next to your COM port. You might see 1410 and the directory of your device. For Linux, that's the same as well. But click on your Arduino Nano or Uno, and now if you press upload, and I won't save it for now, if you press upload, and let's see the pin, and we can see the RX and TX pin flash, and the L pin, the pin number 13, is continuously on, and that's because it's going too fast, approximately 16 megahertz. And if we wanted to blink, then we need another function. We need the function delay. And that's here. If I press delay, it's below. It's down here. Delay. And briefly reading it, it pauses the program for amount of time in milliseconds. Not seconds, but in milliseconds. As the parameter. And unside long. And we'll cover this in part 2 about data types of the workshop. And we want to switch it on and off, which means we need to make the on time some number of seconds, and in this case I'm going to use delay 100 milliseconds, and then the low time, the time when it's off, I'm going to put 100 milliseconds. And now when I upload this code to my Nano, and we also see the TX and RX flash, we can see on the screen, the bottom right hand corner, that the LED is now flashing. And you can have a fiddle around with this and change how fast and how slow it flashes to whatever number you want, which is really cool. And this is handy because recall that on Tuesday your Nanos weren't working, so the fact that the status LED showed that the RX and TX pins weren't working indicated to us as an error. Let's quickly return to the Arduino hardware. I'll cover the digital I/O and PWM as well as the analog pin in a separate slide because they are important for your project. To bring your attention to the max current rating, which is 40 milliamps, it's important to know that you cannot drive a motor with that low of current. You actually need amperes to do that, which requires its own battery source, which hasn't arrived unfortunately. But you can run, you can power up LEDs, a couple of LEDs, not too many, but a couple from the Nano itself, and a couple of sensors. But you have to remember that you can only have a limited number of sensors per pin because you have this max current rating of 40 milliamps. Just beware of that. And we'll move on to next, the amount of memory that you can upload. As far as I'm aware, the Arduino Nanos that were given out have 32 kilobytes, which is fine. But personally, if you're going to use libraries, you might need to be judicious with how much memory you consume, because remember, one character, one letter in one letter such as A, B, C, or D in the English language actually contains 1 byte, which means theoretically the maximum limit that you can upload code to your Nano is 32,000 characters, which is limited. And perhaps I'll also point out that your flash memory is 32 kilobytes, but in actuality you only have 75% of that, because if you recall on Tuesday with the problem of the Nanos and the bootloader, 20 to 25% is used for the bootloader section, which means you can only use 75% of 32 kilobytes. And if you use any external code known as libraries to help you in your robot, then you need to be careful, because if you exceed 75% of your flash memory, then you can run into trouble such as your Nano malfunctioning or not running the code properly. Something to be mindful of, which I found out painfully. SRAM refers to the memory used by your code when it's being executed. You can't actually upload your code onto SRAM. It's for your code to use memory, and it's separate to flash memory. The crystal oscillator refers to the speed, the rate at which electronic instructions are executed. When I say electronic, I don't specifically mean the code itself, because that's different, but the 1 and 0 is the logic gates, and the actual hardware inside the Nano itself operates at this frequency. And EEPROM is usually used for storing static variables, backup data instead of having it in flash memory. It just saves space. That's the point. EEPROM saves space, but we won't be using it. And USART refers to a type of communication protocol which we won't need to worry about in Sumobots. And a quick demo of this is, if we go back to the code, I'll quickly define serial.begin and the idea with serial.begin, serial meaning open a communication, in Arduino means open a communication with the PC, and .begin is a function to tell the Arduino Nano that we want to connect to the PC at a rate of 9,600 bits per second. This is to tell, this line here, line 4, tells the Arduino that we want to connect to the PC at a rate of 9,600 bits per second. Of .begin, and if we go down to communication, which is what we expected because it's going to communicate to our Nano, and if we go to begin, it sets the data rate in bits per second, also known as baud, for data transmission, as we expect, and that's speed, and we only need to worry about the first one. Now the next thing that I'd like to introduce is serial.print, and serial.print states communication. What it does is communicate with the laptop, and I'll put it down there. Print to the laptop, ln, print to the laptop, and it's going to print in something called the serial monitor. It's called the serial monitor because serial represents the type of communication is being used, and that's going to be the laptop, and the monitor is where we see the output from the Nano. Right now I'm going to type in hello, and if we press upload to our Nano, and if we have a look at our Nano, yep, satellite's good. It begins to blink, and if we open our serial monitor, this magnifying glass on the top right hand corner, then we start to see that the TX pin, the top one, is now flashing, and we're getting text outside. And notice how it's 9600 baud, that's 9600 bits per second. If we press this reset button, that is going to reset our program. So if I clear the output, notice how when I press the reset button, it stops. I'm pressing it right now. It stops the execution of the program. That's what it does. And now let's quickly go back to discussing about the Arduino pins. Now, we've got two classes of pins. Oh, and we've got two classes of pins, and they are the analog pins and the digital pins, and I'll explain the difference between them. But there's also something a lot more important too that I need to mention about these pins, and that is to not use the TX and RX pins, these pins, RX and TX. And earlier I mentioned that we shouldn't use them because these pins are actually directly connected to the USB port, which means that if you connect any information, any signal to these two pins, you can actually interfere how you communicate with your laptop, given that it's connected. So I'll demonstrate to you right now, and right here I have a Bluetooth module, and I'm going to quickly hook all the pins up and show you that you can interrupt. You can actually cause the Nano to not respond to the laptop if you use the RX and TX pins. And let's do that right away. And red is 5 volts, and as a heads up, it's a good technique to always label your positive terminals, or VCC, this voltage, as red, and your ground as some dark color. In this case I've chosen brown. Put that ground over there, and I'm going to hook up the input and output pins from the Bluetooth module, which is orange and green, to RX and TX. And I'll quickly change to my code to show everybody. Okay, so I'll open the serial monitor as well. Whoops. So it's printing out hello. Now, the moment I put in these two pins, okay, that seems good. So we're still getting some output, but if I try to upload, so right now the Bluetooth module is blinking, which means it's trying to transmit a signal. And just briefly, yeah, there was something gibberish there. If I try to upload my code to my Nano, it's out of sync, and the reason for that is because I'm connected with the Bluetooth, and it's interrupting the transfer signal from my laptop, and that can cause bugs. But fortunately, the code is still running. But if you wanted to upload your code, then you couldn't, because you're actually you're transferring a signal to TX and RX, and that's blocking the laptop's way of transferring a signal. So we actually need to do not use RX and TX. And this is a common bug. So that way we can upload our code. And if I do that now, removing RX and TX, everything is fine. And that's purely because of Arduino Nano's design. I'm going to return and explain the reasons for having analog and digital pins. And the reason for that is because in the real world there are many different types of signals. And consider, for example, a thunderstorm. You have different voltages between the sky, the cloud, and the ground, and they alternate in a range. This is considered to be an analog signal, or another analog signal is your electromagnetic wave, light. It varies in between, and it doesn't exist between ones or zeros, such as a digital signal, which is considered to be discrete, on or off. Now, because of that, there will be two main signals in the Arduino that it can handle, and that would be the digital, where there are two possible states, either low, where it's 4.5 volts or lower, or high, when it's approximately 4.5 volts or higher. The reason for 4.5 volts is a hardware implementation, which is a rabbit hole in itself that is irrelevant for Sumobots. But there's also the analog signal in the Arduino, where there are many possible states ranging between 0 to 5 volts, the maximum voltage. And I'll quickly run down the differences between the analog and digital pins. And the analog pins can receive analog and digital signals, but they cannot transmit any analog signal, only digital signals. That's very important. Digital pins, however, can only receive digital signal and only transmit digital signals. In other words, the digital pins can only work with digital signals. The analog pins, interestingly, are semi-analog, because they can receive analog signals, but they can't transmit. They can't get output analog signals. And because in Sumobots you're going to try to move your robot around, that means changing the speed of your motor. That raises a big question. How can you only control the speed and direction with only ones and zeros for your robot? And there's a good solution for this, because we use pulse width modulation, and that's by changing the width of the square wave by changing the on time versus the off time, and doing so effectively changes the average voltage seen by the appliance, as you can see with these three diagrams. So at 25% of a duty cycle, as we see here, 25% of a duty cycle of 12 volts, that's an average voltage of 3 volts seen by the appliance. And 50% on and 50% off, then your average voltage that's seen by the appliance is 6 volts, because it's 50% of the duty cycle. I'm going to show the definition of the duty cycle in a moment, but I just want to point out that changing the percentage of the duty cycle means we can change the average voltage seen by the motor, and in turn we can change the speed and direction. And to point out, the frequency of a pulse width modulated signal is constant, and on the Nano there are specific pins that have 980 Hz and 490 Hz. And the formal definition of PWM is the on time divided by the period of the wave. In this case, the period of the wave is given by these lines here, these dashed lines. And so this is 25% of the period of the wave, and that will give you your duty cycle. The duty cycle also happens to be mapped by the Arduino Uno, where the value from the Arduino Uno is between 0 to 255. This is going to be used in one of the functions that we use afterwards, and the reason for this range is because the Arduino Nano is an 8-bit machine, meaning that it will process it'll have a range of 2 to the 8 minus 1 values. And aside from the theory part, I think it's best if we practice some problems, but I think there's something else that I need to cover, and that's there are only a limited number of PWM pins, and it is the ones indicated here, 11, 10, 9. Sorry if I'm feeling slow, I'm actually rather sick. So you've got 6 PWM pins as indicated earlier in the table of the 14 digital pins. So you have a limited amount, and that means you need to use these pins wisely when you want to control your motor. And if you consider adding or changing the number of motors you have, then you have to remember you only have a limited amount of pins, PWM pins, that can allow you to control the motor. Now, with the theory aside, let's apply these principles now to make an LED change brightness. And to do that, we'll first need to look at the reference implementation for the Arduino functions. We return to the main page, and similar to the digital read and write functions we explored earlier, we also have the analog read and write. We won't cover reference. We're more concerned with reading and writing analog signals. Just bear in mind, the Arduino can't transmit, it can't write an analog signal. What it can do is, remember, use PWM to make a square wave that changes its width. Okay, let's have a brief read. Analog read. Right, now I've just built my circuit, and now let's head back to the code, the Arduino IDE, and begin coding. So we'll make a new sketch, which is just another name for code, and we want to increase and decrease the brightness of the LED. First, we should make a comment that tells us what we need to do and what the code does. Increase and decrease brightness of LED. And first we need to define the pins that we're using, and according to the diagram, which I will let me get it back. According to the diagram, we need to move connect pin 6 to the black LED, and we're going to use that one. So we'll use pin mode, and we want 6 to be, even though we've connected it to 3.3 volts, the average voltage seen by the LED will actually change. So it still has to be an output. Sorry, I'm getting sick. Output. That's it. Now we want to increase. We'll start off by first increasing the brightness, and we'll use the analog write function, and let's see what it does according to the reference implementation. It writes an analog value, PWM wave, to a pin, so the wave that we mentioned previously. And after call to analog write, the pin can be used to light an LED at varying brightness or drive a motor at various speeds. This is important that we're going to do afterwards. And after a call to analog write, the pin will generate a steady rectangular wave of specified duty cycle, as I mentioned before. But let's look at the parameters and syntax. We need to give it a pin, and we need to give it a value. And the pin is the thing that we write to, that we send data to. And the value is the duty cycle. 0 always off and 255 always on. And recall that I showed you that the duty cycle for the Arduino is between 0 to 255. That's basically the same as the former definition as before. We're just now mapping it between the 8-bit range of the Arduino. Now let's have a go at changing the brightness. We're going to use analog write 6, and then we'll start off with high, and we use delay. And don't forget, because we want to be able to see the brightness change, we need to add a delay. Gonna add 50 milliseconds. And the next thing I'll do is change the value, and I'll copy and paste it. And now that's going to be, let's say, 250 milliseconds. I'm going to decrement by 50s. That's 150. That's going to be 100. That's going to be 50. And finally 0. And that will be how we change the brightness of the LED. Let's upload it to our Nano. As you can see, we've successfully changed the brightness of our LED. It's flickering on and off. And we could extend this to make a smoother change in brightness, but I'm going to leave that for next time, for next workshop, and leave you with a challenge problem for you guys to do. And this challenge problem requires you to match how the LED flickers, how it changes brightness. And I'll post it now.